For this video, I want to go through some of the answers of the problems that you worked on in class. So for the first question, it mentions two skiers who have the weight of 525 newtons each are sitting on a chairlift with a weight of 2,500 newtons and are moving at a constant velocity. You were expected to focus on the chairlift, write an interaction diagram as well as a force diagram for that. So let's start with an interaction diagram for this one. And it might be nice just to refresh our memory in terms of what sort of forces we're dealing with. We have contact forces and we have non-contact forces. We have normal force as a contact force. We have tension and we have friction. And for non-contact forces, we have gravity. All right, so now going back to this diagram, you know your focus is the chairlift. That includes all of this part of the chairlift. And you're going to ask yourself what things are touching the chairlift. So clearly there is a contact between, there's a contact between this rope and the chairlift, and you also notice that these people are touching the chairlift too. So let's talk about what that is, which types of forces those are, and see if we can work that out into the force diagram. So these people seem to be pushing down on the chairlift. So I would say both of those are normal forces, and they are pushing down. I have one person pushing down, and I have another person pushing down. And for that reason, each of these people has their own vector, okay? I also know that the number of newtons of these people pushing down is 525 newtons each. So we'll just write that over here, 525. Goodness, it always does this. Okay, next thing is you notice up here we have also a type of force. Now it's going to depend on how you see this. You might see this as the rope is pulling the chairlift up. Sometimes for those of you who've gone skiing, you know that it actually sits on that chairlift, but that's fine. Let's call this a tension force, that the rope is pulling this up. Tension. And so for that reason, we're going to have this be an upward force. All right. Also, the other piece of information is we know that there is gravity, so we'll put the Earth here. And there is a gravitational force. And this gravitational force is a downward force. So looking at what we've drawn already, and this is why those interaction diagrams are so important, it looks like we're going to have four vectors, one for tension, two for normal force, and one for gravitational force. So let's draw that as a force diagram. All right, so let's do gravity. Gravity is between, so that's the force of gravity between the Earth and the chairlift. And that has 2,500 newtons of force. I also noticed, as I said, that we have two normal forces pointing downward. Yes, you do need to show both of those vectors. This is a normal force from a person, we'll call him person 1 on the chairlift, another normal force from person 2 from the chairlift. Each of those people is applying 525 newtons of force. I'll write that over here. All right, now I know this object is at constant velocity, so that tells me I need to draw a balanced force diagram. So with that said, what I need to do is I need to add my numbers here, 2,500 with 525, and again 525. And that works out to be a vector that's just as long as the one pointing down, and this is what I called my force of tension between the wire and the chairlift, and that is 3,550 newtons. Okay, couple of things I'm noticing that people are struggling with. Be sure your focus object is always the last letter. Notice how I have C as my last letter for all of these. I have my force, always starts with force, the name of the force, tension, and which object is actually causing that force. So that's for my first one. Let's move on to the next one. So here I have a Sharks hockey player who has a weight of 800 newtons. He hits a hockey puck. The hockey puck is 3 newtons in terms of weight and travels at a constant speed. Ooh, that's a key term, of 170 kilometers per hour. So constant speed, instantly I know I'm dealing with something that needs to be balanced, okay? So we have balanced forces. Now, this hockey puck right now is not being hit. It has no longer contact. It is just speeding along. So let's see what objects are touching this hockey puck. So at this point, you notice that there's really only, I'm going to change my pen color here. There's really only one object that's touching it, and that is this ice right there is what's touching it, okay? So it is pushing the hockey puck up. For that reason, I know it is a normal force pushing it up. The only other force I have is gravity, okay? Oops, let's call that the Earth. And so this force here is gravity. Now, a lot of people think, oh, I have a force that needs to move this direction because it's moving that way. No, it isn't, okay? Only if it touches it does it apply a force. And the only thing that's touching it right now is the ice. So in this case, I know gravity is pulling it down. I only have 2 vectors. So in this case, my force diagram is going to be where I have gravity pulling that hockey puck towards the center. So here is gravity, and I'll have it be the Earth to the hockey puck. And the other vector I have, and I'll try to make it, there we go, is my normal vector. And in this case, it is the ice pushing up on the hockey puck. So I know that the hockey puck's gravitational pull is 3 newtons. It has to be balanced, so that means that this normal force is 3 newtons as well, okay? You notice that I'm giving you a piece of information that's not even important. So you have to be sure you select only the numbers that are actually touching the object. So for this one, I am going to have you take a look at the kite. If you take a look, it was a kite that was being flown, and I'm doing a rough stretch here from a person, and the person was holding it from the side, okay, and was being dragged along. So that's going to be some important information. The kite is not above. All right, with that said, changing pen colors again, maybe to red, you have here this kite flyer, and she has 2 strings on the kite. For hers, she is the focus object, and so we're going to create a force diagram based on her. So let's start off. We know that we have the Earth, so that's always an easy connection. We know we have gravity. All right. Next one is, you notice that she's touching the sand or the ground. So if she's touching the ground, that means that we have some sort of force. The ground, what is it doing to her? It's actually pushing her up, so we call that a normal force, okay? It's actually pushing her up. So we will draw our arrows. Gravity is going down. Okay, next thing. You notice here we've got them holding the string. So on one hand, she's holding 1 string. So that is, and it's pulling her, all right? So that pulling force is a tension force, and it's pulling her this direction. You notice over here we have another string that's pulling her. For each object that she's touching, you need to include that. So there is another tension. Because it tells me right here she is moving at a constant velocity, I need to make sure I have a balanced force diagram. It has to be balanced. And you're noticing all of these are balanced. Yes, they all are because they're all moving at a constant velocity. So let's quickly do the force diagram for this. So we have gravity, Fg, between the Earth and the person. All right. It looks like she has a mass of 500 newtons. Excuse me, a weight of 500 newtons. That means that her normal force, which is our upward force, is going to be equal. So we have a normal force between the ground and the person, which is 500 newtons. All right, next thing is you notice we have a tension force. And it looks like the tension force is 80 newtons each. So we're going to create two vectors. Why am I creating two? Because look, I have 1, 2. Each of those vectors is going to be a force of tension between the string and the person. Again, force of tension between the string and the person. And this is 80 newtons, and this is 80 newtons. Now, is this a balanced force diagram? And the answer is no, because you have a force moving this direction but not in this direction, and it has to be balanced. So we're going to assume that the other force that's opposing that is going to be friction, and that's going to be between the ground and the person, and that has to be 160 newtons, so that these vectors are equal. 80 plus 80 is the same as 160. We now have a net force of 0 newtons. Okay, all of these will have a net force of 0 newtons. Okay, moving on to the next one, and this will probably be the last one for this video, and then I'll do one more. Here we have Vincenzo, who is winning the Tour de France. He gets a flat tire, but keeps on riding 335 kilometers east. Okay, so we're going to have the focus be the bike. Let's change pens here. All right, so we know first of all that we have the Earth here, so there is a gravitational pull. We have that. We also know that the bike is touching the ground. That is a normal force. Okay, that means the ground is pushing up on the bike. What else is pushing on the bike? What else is touching the bike other than the ground? Well, the person is. So this person here, what is he doing? He is also pushing now down on the bike. So that's a normal force pushing down. Okay, we know that he has a frictional force of 75 newtons. That means between this tire, the one that's flat, I think it's this one here, friction, we have a frictional force, and it's slowing him down by 75 newtons. Okay, but he is moving at a constant speed, correct? There it is. So that means that he needs to have a pushing force, maybe thanks to the pedal, his foot right here. That foot is pushing, and that is a normal force. Okay, so let me just kind of point that down to that foot pushing on the bike and having a normal force. All right, so let's quickly draw the force diagram on that. So I know that I have gravity, and it looks like force of gravity between, again, the Earth and the person. And it tells me that Vincenzo is 400 newtons, very light. And then we also know that we have a normal force pointing downward, which is Vincenzo sitting on the bike. Oh, and my apologies, this should be for the bike. Our focus is on the bike. So Vincenzo is applying a normal force, so that's the person on the bike. Remember, our bike is our focus. And it looks like, let me try this again, my apologies. This here, let me erase this. Okay, let's try that again. Okay, so based on the bike, we know we have a gravitational force. Oh, it seems to be redoing this, so we'll just go like this. So we have a gravitational force of 50 newtons between the Earth and the bike. So that's 50 newtons. I then have Vincenzo applying a normal force on the bike, so that's the person on the bike, with 400 newtons. We have an upward force, the normal force being the sum of that, 450 newtons of Fn force between the ground and the bike. And then I also know that I have a frictional force of 75 newtons,